Welcome, everybody. It's a fantastic day. And of course, as always in high summer, this is the place to be. Nowhere else, especially when we got a title like today. So it's my pleasure to welcome Flor. And for the formal introduction, I'm going to hand over to her guest, Professor Mappelli.
Thank you. So, hi, everyone. Thank you for being here and not outside in this beautiful day. And it's a pleasure and an honor to host Flor Broekgaarden. Her biography is quite short, but really spectacular. So Flor obtained her master in physics and astrophysics in Amsterdam in 2018. Then she Harvard University for her PhD, and she obtained, can you hear me? Anyway, and she obtained her PhD in 2023, so basically last year. But after that, she became, I think, okay, she became, thank you so much. She's a very kind person. She became junior fellow in the Simon Society of Fellows, jointly at Columbia University and the Flatiron Institute in New York. And assistant professor at Johns Hopkins University in Baltimore, but she didn't even make it to Baltimore because last week she studied as an assistant professor at the University of California, San Diego. And in the meantime, she also managed to get a Hubble Fellowship and the climate, a Miller Fellowship and the climate, and many other things. Her work is mainly in the field of data science, gravitational waves, population synthesis simulations of massive binary stars, and putting all of this together. So, Flor, the stage is yours, especially if you manage to have one mic.
Thank you. Does this one work?
And 11.
Such an eventful day already, you know. I'm sure maybe this helps like keeping everyone awake, but yeah, it's a great honor to be here and see actually many lovely friends actually from my time in Amsterdam, such as Javier, who I did my master's with. So yeah, it's really a pleasure to be in Heidelberg. And today actually my talk is going to be about gravitational-wave paleontology. And this is because I like this title, because for me, basically, massive stars are the dinosaurs of our universe. And that's the case because I think similarly to how paleontologists use fossils to study the formation, lives, and deaths of dinosaurs, I like to use the fossils of these massive stars, black holes, and their observations of gravitational waves of these black holes and their black hole collisions, to understand how these massive stars once formed, lived, and died throughout our cosmic history. Okay, so how does it work? Well, some of you might know, but for everyone else, compared to our sun that's shown here, the massive stars that I like are these stars that are usually at least 10 to 200 times the size and mass of our sun. They're extremely rare to find because they live fast and die young. So their lifetimes are typically 1,000 times shorter than the life of our own sun. And they're also extremely rare among stellar populations. So the initial mass function usually tells us that for every 1,000 stars that we see, maybe only one of those stars is born as a massive star. And so combined, these two basically means that they're extremely rare, these massive stars, among stellar populations. Overall, these massive stars are extremely rare among stellar populations. And so combined, this means that it's extremely difficult to study and find these massive stars in our own Milky Way. And especially this is true when we try to find and study these massive stars in more distant environments, like in many galaxies much further away, where we often rely on very, very expensive surveys or expensive telescopes like the James Webb Telescope that often cannot resolve individual stars, but only really look at integrated populations or an entire galaxy population of stars. And so this is why actually today there's very little known about these massive stars. But there's one thing that we do know, which is that they play an incredibly important role for shaping our universe through all these different processes. So for instance, they trigger and trace star formation. Their strong winds provide like feedback that enrich their environments. They cause these incredibly interesting transients like X-ray binaries. They often outshine galaxies, especially in the early universe, or like the dominant source of light. They form these supernova, and when they die, they explode. And also, for instance, form black holes and neutron stars. And in case you didn't know, actually, these massive stars, and you should definitely ask Eva, who's like the expert on this, they actually make many of the heavy elements in our universe. And so, for instance, they're actually responsible for creating all the oxygen that we breathe here on Earth. And there's one thing that we actually do know about these massive stars now, as of maybe 10 years or so, actually. And that is that they often form and live in pairs. And during their lifetime, they interact. And so these stars, they maybe rotate, they can like interact and like exchange mass during their lifetimes. And these massive stars, when they explode, and if they can stay together, they undergo like these explosive supernova. And so one can go supernova, the other one can eventually, after a while, also go supernova. And in a very, very rare case, which is extremely rare and difficult, that they stay together after those explosions and throughout the rest of their life, they can actually form pairs of black holes, a binary black hole. Now, I didn't have the budget of Interstellar to make beautiful visualizations of black holes. So instead, I did it with marbles, visualizing these black holes with marbles. And so if you have a pair of black holes, these black holes will eventually collide and get closer and closer together after billions of years, and eventually form one more massive black hole. And as of 2015 or 16, when LIGO and Virgo observed these first collisions of black holes, this made like astronomers like me wonder, can we maybe use these fossils, these collisions of black holes that we observe, to then learn and figure out how these massive stars once formed, lived, and died, and use them kind of as fossils. And so this is a field that we have started to call gravitational-wave paleontology. So using these black hole collisions to understand how these massive stars formed, lived, and died throughout space. Now, okay, so how does it generally work? Well, gravitational waves, you have two black holes that are eventually colliding, during which they produce these waves in space-time itself that travel over millions and millions, and like hundreds of millions of years, until they finally reach us here on Earth, where they basically like stretch and squeeze Earth itself. Here it's a little bit exaggerated. But we can actually pick up these like tiny signals with LIGO and Virgo with these laser interferometers, in case you haven't seen this. And so from these like small wiggles and these interferometers, LIGO and Virgo can actually observe these gravitational waves through these like chirps that you see here in blue. So some time and frequency event. And from these observations, they can actually infer the properties of the black hole collision. So things like their masses, their spins, mass ratio, and how often these collisions occur in the universe. And there's one really cool, fascinating thing that I think makes gravitational waves really, really interesting for studying stars in the past. And this is the following. So if you kind of take the universe, then you start with the Big Bang. This is probably a classic picture that you've seen. The first stars form maybe here, and then you have all the way on the right, kind of the today. And so there's all this like star formation and galaxies that's happening. And actually you can kind of like put this in like a year time scale. Like if this was like January 1st of a year, and this was like December 31st of a year, you know, you can kind of like split it up. And one thing that's interesting is that because maybe these stars, they actually form pairs of black holes in maybe just a few million years, they die very, very fast. It might actually take billions and billions of years once you have a pair of black holes before these black holes actually collide, and we observe them today. And so this means that when you are LIGO and Virgo and you're here today looking into the universe and observing these gravitational waves, these black hole collisions, even if you observe the local black hole collisions, which is what LIGO and Virgo are doing today, you're actually probing, or might be probing, these stars and progenitors that once formed them from much early in the universe, possibly as like early as the first star formation or even beyond. And so this is why we're super, super excited that we might actually probe and use gravitational waves to like probe massive stars in the past and probe individual massive stars in a way that's just not possible with any other survey that we have. Because for instance, in the Milky Way, either all massive stars are like kind of higher metallicity, and so not like formed in the early universe, or they have already died and formed black holes, and it's much harder to find them. Okay, and so in principle, we're happy, right? Like we have the gravitational wave collisions, we can just map that back to the pairs of massive stars. Well, it turns out that it's really, really difficult that once you have pairs of black holes to actually go back and immediately learn about the stars. And this is because the black hole collisions don't directly like imprint the properties of the stars. And so instead, what we do in practice is that we basically have to like forward model how these stars live and evolve to then compare it with the observations of gravitational waves. So see it a little bit how maybe a paleontologist is like trying to figure out if dinosaurs have feathers, but the fossils themselves don't leave immediate imprint of the feathers. But you can kind of model like dinosaurs with and without feathers and see what kind of fossils they leave behind and then compare it with the data. So we do exactly the same. And typically what this looks like is that we call this kind of population synthesis stellar evolution. So we're trying to evolve large population of stars that could have lived all throughout our cosmic history and see what kind of black hole collisions they form. And so typically that looks something like a factory where we use like kind of a code or simulation that takes in pairs of different hypothetical stars with, for instance, different masses, here mass 1 and mass 2. And then this code takes care of things like stellar evolution, binary interactions, and calculates whether that specific pair of hypothetical stars formed a black hole collision, yes or no, and comes out like successfully. Now, of course, this is not what our simulations look like in practice, but in practice we have some code. For instance, I work a lot on like Compass, where you enter some pair of stars with different initial conditions, so things like masses, separations, eccentricity, metallicity. And then in this code, there's like some C++ or Python or Java code, etc., that takes into account the single star evolution. So how does a single star just evolve? But then also all these like other interactions and physics that you have to deal with when you think about massive stars and pairs of massive stars. So things like stellar winds, mass transfer and how stars can exchange mass, common envelope evolutions, and there's also like supernova explosions, things that Fabian Schneider works a lot on here. Okay, and of course there's not just one code, but in practice there's all these different codes. These are a subset of them that all kind of have their own favorite prescriptions or their own treatment of doing this, basically. And you can listen to whole other talks about all the differences between the codes and whether, should we have that many codes? That's very interesting, yeah. But okay, so you could say, you know, we were thinking about this picture. We now have these codes, and these codes actually, they often use parameterized prescriptions for all this like single and binary stellar evolution. And by doing so, they can actually run a single binary system, so one hypothetical binary, often under a sub-second. So it only takes like a second or less to give it one pair of binaries, like one binary system, and it will tell you, okay, it formed a gravitational source or it didn't form a gravitational source. So based on this, you could think, okay, all good. We have our code. We can forward model all these stars. We're happy, right? We can do gravitational-wave paleontology. Well, if there's one thing I hope you remember from this talk, is that in practice, this step of forward modeling these populations of stars is actually really computationally challenging. And this is because there's basically 5 big barriers that we have to overcome in order, and these are like computational barriers in order to fully and truly model populations of stars in this way. Okay. So what are they? Well, the first barrier, and I call this like the uncertainty challenge or uncertainty challenge, is that there's actually a lot of uncertainty about the formation pathway, like how do you form actually these gravitational wave sources? And so there's many theories that have been proposed for how you can make a pair of black holes that can then collide and be found. And so, for instance, a common theory is that maybe they form from these pairs of stars, like wide binaries that we call isolated binary evolution, in which you maybe start with a binary pair that then undergoes some like mass transfer. It then ends up as like a strip star, again, as Eva, that goes supernova. And if it survives, it might leave behind a black hole. Then the second star might evolve. There might be like an X-ray binary phase. It might then enter another mass transfer phase that might then be unstable and lead to this common envelope phase, in which basically the core of the star like slowly like drags closer towards the black hole. if it survives this and successfully ejects the envelope, you might end up with this closed binary of a black hole and like a strip star. And if the second star goes supernova, for instance, it might leave behind eventually two compact objects in a binary. So here it's a black hole neutron star, but it might also be like two black holes or two neutron stars that can then collide in a Hubble time and be seen by LIGO Virgo. But of course, this is just one channel, but in practice, there's all these different channels. So for instance, maybe they instead come from these population 3 stars. So these stars very early in the universe that are much more lower metallicity and stay small. Or maybe they actually come from like triples or quadruples. So where you have 3 or 4 stars, where the third or fourth star can actually help the other stars get closer together. Or maybe instead they form more like dynamical. So maybe they form in these like dense environment that have like lots and lots of like black holes that can like undergo all these like 3-body interactions, such as like an AGN disk or globular or open clusters. And then of course there's like some other interesting channels like primordial black holes, or maybe there's like some flyby and they catch like a star. But all of these can also be mixed. But the big challenge is that like we're not sure. We're just not sure which of these channels it is, and they all come kind of with their own predictions. So at the moment, what you would truly have to do is not just like model it for one channel, but basically rerun your simulations, modeling all these different formation channels, and that already becomes much more computationally expensive. Okay, so that's the first challenge. Now, the second challenge is that actually the initial conditions of the stars that can make pairs of black holes is really, really uncertain. And so I started with these like, you know, you can have different initial masses, but there's actually many initial conditions that can be different and that are uncertain, such as the metallicities. And it turns out that these initial conditions can have a drastic impact on whether you leave behind, for instance, a pair of black holes and what a pair of black holes looks like. So here's, for instance, a plot from actually Michaela and others, where you can see that based on initial metallicity, so that's here in the rainbow colors, if you ask like, okay, what is the total mass of the binary black hole that is left behind by such stars, it varies very different. Like it varies a lot depending on which metallicity you begin with. And so what this means is that instead of just trying 2 different hypothetical masses for these stars, you actually have to try out all these different initial conditions and like explore this entire parameter space to fully explore which stars leave behind which pairs of black holes. And so that adds, again, extra computational cost because you have to like simulate many, many more binaries with all these different properties. In addition, and this is maybe one of the other big challenges, is that these gravitational wave sources are extremely rare outcome of stellar evolution, both in real life, like the real universe, as well as in these simulations. So often what happens if you start with maybe 1 million binary stars with different initial conditions that you try in your simulation, only a small fraction all the way here at the end, like maybe 1% or so, or a few percent, ends up as a gravitational wave source. And so most of the binaries that you try and the computational time that you spend is actually wasted on things that you're not interested in for your population. And so in practice, what you have to do is you have to run your simulation much, much longer to still get like the right number of interesting events, so gravitational wave sources, to compare to observations. And so in the past, this has really led to some like kind of Poisson or sampling uncertainty in cases that you don't do this. Now, the fourth challenge is that this stellar evolution and stellar evolution in general is like very uncertain. So I showed you like one example of a pathway to form a pair of black holes or black hole neutron stars in this case. But of course, all these different phases in massive star evolution is extremely, extremely uncertain. And so in practice, what you have to do is that we model all these phases with these like parameterized prescriptions. And we would have to vary some of these like assumptions for these parameterized prescriptions. So maybe there's a prescription that, for instance, says how much mass transfer there is from one star to the other star that we have some free parameter for. And so what you ideally want to do is like rerun your entire simulation, but while varying some of this like uncertain assumptions in your model. And this becomes really, really computationally expensive because there's many of such parameters and the parameter space becomes extremely large. So again, you have to like rerun your entire simulation and like redo everything. And the last barrier is maybe somewhat the most important, but also impossible barrier sometimes, which is that stellar evolution and binary star evolution is really, really uncertain. And so, for example, in our codes, we model this common envelope phase with a simple prescription that has these 2 free parameters like alpha and lambda, and then some like conditions based on like the masses and like the radius of the star. that we use. Like this is the entire equation that we use to decide, okay, how does it like go through this common envelope, and what is the binary, how does the binary end after the common envelope? Where of course in practice, if you see some of the detailed simulations like Javier is doing, you actually see like if you do hydro simulation, that is a much more complex and like dirty process where you just have like much more physics that cannot be captured by such a simple analytical prescription with just 2 free parameters. And so what we should really do is like replace some of these like simple prescriptions with more detailed hydro codes, for instance, and like the solutions from these hydro codes. But that becomes really expensive because these analytical prescriptions are almost like free, and these hydro codes can sometimes take like weeks, if not years, if not months, to actually simulate one single system. So it's basically impossible to replace that. And so all in all, these 5 challenges means that the total computational time that you need to do all of this and to properly explore the parameter space and properly do simulations is just like billions and billions of CPU hours, like billions of years of CPU hours. It's just impossible to do them all. And so all current studies often like limit themselves by often at least 4 out of 5, not doing 4 out of those 5 things, explorations. And so sometimes if you ask me, what does it feel like to do a gravitational-wave paleontology? I maybe feel more like this, where I'm just like trying to kind of like overcome some of these hurdles, like all of us are. But you're just kind of like failing over each next hurdle as you go. I hope the Olympics will look a little bit better than this. Yeah. And so I think it's a really important question that people are asking in our field, is that like with so many uncertainties, like on top of uncertainties, is there anything we can do? Like, can you actually learn about massive stars from gravitational waves? And I think that's a really important question. But I have some hope. And so with my group, one of the things that I'm really trying to do in the coming years, and as are many people in our field, is to really start tackling this by first identifying and like quantifying what some of these barriers are, and then hopefully like moving forward with the help of a lot of the other astronomers in related fields to hopefully address them and eventually tackle them and make better models. And just to show, here's like some of the people of my group, and I'll show some of their work during the rest of the talk. Not like this logo. Yeah. But anyways. Okay, so I'm just gonna sample a few examples from things that my group is working on, as well as like things from recent literature. That's kind of state of the art, but it's like impossible to like truly address all the things that the field is doing. But happy to discuss more things if you ask me. Yeah. Okay, so let's go. What about these uncertain information channels? Well, we decided about a year ago, and we're actually updating this soon, to kind of first ask, okay, if you have all these different formation channels, how much can you tell about which formation channel? For instance, already based on the current LIGO Virgo data, like which formation channel is at play? And so one thing that we made this incredibly large overview of all the current simulations that are out there from all these different formation channels. And we focused on one quantity that people measured in gravitational wave, and that is what's here on top. So this is showing the local black hole merger rate density. So it's just how many black holes are colliding per gigaparsec cube volume per year, so per time. And basically, if you ask LIGO and Virgo, what they do is they observe basically about 100 black holes collisions that they found today. They know to which volume they're sensitive to, like how deep they can look. And so based on that, they can kind of say, okay, 100 divided by the volume, divided by the number of years that we've been observing, they get some rate. And currently the rate from observations lies somewhere between 10 and 100. So these are different estimates of that rate that are use slightly different assumptions within LIGO. And so what you can do is that, okay, LIGO finds 10 to 100. Now, what about these simulations? So if you pay attention for 1 minute, you'll now see 200 papers, which might be a nice outcome of today. And so it's actually gonna go through all these different formation channels. So here, each color, so here green is a different formation channel. This is from pairs of massive stars. And now each horizontal line that you see is basically one person, like one PhD student or one postdoc or maybe one professor that's like been sweating and like run their entire simulation of a population of stars, then maybe changed some of these like hyperparameters like this alpha or beta in their simulations, rerun the entire simulations and then found like a slightly different rate. And then a line between those scatter points that you'll see are then like basically the range. It's just to indicate the range of these simulations from one paper. And so each line is like another paper in the field. And so what you see, I hope, and this is for neutron star black holes now, what you see now is that, okay, there's some channels where we don't have that many estimations, but there's many channels where the lines actually kind of go through like orders of magnitude in rate in their estimations. And even disagree with each other of like what the rate should be. So should it be like upper limit or should it be as low as that? And so for instance, this is for binary neutron stars where the rate is like between 10 and about 1,000. Nice thing for binary neutron stars, we also have other observations like gamma ray bursts that we can compare to. And they kind of agree. But then if you compare it to like theory and simulations, you'll see that there's these like enormous ranges that like 5 orders of magnitude, even for the same formation channel here, isolated evolution, that we think this rate might be. And even if you look at other channels, that there's a lot of overlap. There's a lot of channels that still can kind of make the same rate as the observations. And so overall, our conclusion was twofold. So first, that there's a lot of uncertainties in these simulations that make and cause these orders of magnitude differences in like this rate that you get. But also that based on the rates alone, it's basically impossible to rule out formation channels or say which formation channel contributes the most at the current date. So one thing that people are doing, including one of the students, actually this paper is now published, is that we're interested in like, okay, but that was just a local rate. So far we were just comparing this number that's on this like, the redshift is 0 axis. But what about if we look at the rate as a function of redshift? And so one of the interesting things that we're finding is that then the rate as a function of redshift is much more robust for a certain channel. So here you can see that like maybe the total or absolute rate can easily like change orders of magnitude or like 1 or 2 orders of magnitude. But the shape of this rate, and these are all based on one formation channel, isolated binary evolution, is kind of the same. Like it always goes up, then peaks around the peak of like star formation, and then sharply goes down. And so this is interesting because maybe it means that if instead you don't just look at this local rates, there's like one number that's you get on this y-axis, but instead it's like this extra dimension of like, okay, what about the redshift evolution? You can maybe start finding like differences between, in this case, like different formation channels based on different behavior. But of course, it becomes more and more challenging when you start adding different simulations that make different assumptions. So again, we're hoping to start making a catalog with all these like different dimensions and different rates. But it's really challenging to include all the uncertainties. But there's some hope. Okay, what about the uncertain initial conditions? Well, there's a lot of people in the field that are trying to map out and quantify how different assumptions, for instance, here for the star formation history. So like how many stars are forming throughout the universe and with what metallicities do they form, how that impacts the rates. And so, for instance, there's been some nice work that, for instance, shows like different lines for 4 of these different assumptions. And here's like a whole catalog of lines that basically people have used to start quantifying that. And the same you can actually do for not just like isolated binary evolution, but also for all these other formations. So people have started to do it for like population 3 stars, which is really nice work. And then also for like globular clusters and other channels to kind of start quantifying how much this impacts the results. And actually with a student, again, we're doing a big project where we're using these cosmological simulations from CAML. So it's trying to basically use like all available cosmological simulations to kind of see how does that impact different rates of, in this case, binary black holes across redshift. Okay, so what about this third hurdle? They're extremely rare in simulations, these gravitational wave sources. And so for that, both me and other people are kind of working on these, like, maybe we can improve maybe we can improve our simulations for how often we get these gravitational wave sources out. And so a while ago, I actually wrote an algorithm that I called stroopwafel after a Dutch cookie. And in principle, it kind of works like playing a game of battleships, where you're trying to guess, usually in a game of battleships, like where the locations of the ships of your opponent are. And in principle, you could do this completely random, like guessing a completely random square the next time. But probably most of you actually use this like tactic on the right, where maybe once you find a hit, you sample around it and like kind of zoom in. And so this is like a well-known technique in machine learning and AI where it's kind of like grid refinement or importance sampling and so on, like Markov chain Monte Carlo, where instead of just completely randomly sampling, once you find like the events of interest, you kind of zoom in your simulations. And so we wrote a very similar algorithm, but now not to find battleships, but to find the locations or the initial conditions of these pairs of massive stars that can lead to gravitational wave sources. So now maybe you have a grid where you have like different masses of the hypothetical stars. And then the islands that you're trying to find are like the initial conditions, so the combination of masses that actually lead to gravitational wave sources. Of course, it's much harder because it's a much higher dimensional space. And these islands have like unknown shape and an unknown rate. So that makes it really, really, really challenging. But one of the fun things is that like with some collaborators, we could actually improve this method and make it work in really, really high dimensions and make it so that it actually speeds up our code by more than a factor 100, kind of helping us out with some of these computational challenges. And there's a lot of people trying very similar techniques and trying to apply machine learning and like neural networks, normalizing flows, etc., to kind of speed up these simulations and help with the computational cost of finding these events. Okay, so what about some of these other barriers that we worked on? So one of the other things that we did is like we were very interested, now that we could speed up these simulations, in quantifying like how much some of these uncertainties in stellar evolution and these uncertain initial conditions like affect the results in our simulations. And so one of the things we did is that we kind of looked in like, okay, how do these two classes of uncertainty impact, for instance, the rates of different compact object binaries? So in this case, it's for black hole neutron stars. And basically on the y-axis, you have this rate. So this is the observed rate. And on the x-axis, it's gonna like scroll through different models. And so what we find is that like, okay, maybe in the past, people kind of often only did like one simulation or a few variations. But if you truly try to like vary from all these uncertainties, you get something that's much more like this. So now as you go on the x-axis, you're kind of varying in your model different stellar evolution assumptions. So things like mass transfer or common envelope assumptions. While on the y-axis, you're kind of changing things like the star formation history. So how did the universe form stars and with what metallicities did they form them? And there's some interesting things that we found and like many people found after us, which is first of all that like they both can really impact these rates, but also that they kind of impact the different flavors of gravitational wave sources very differently. So maybe this is for black hole neutron stars, but for binary black holes, it looks much more flat. So you see that actually the stellar evolution uncertainty doesn't really impact these rates, but the cosmic model does. Whereas for binary neutron stars, it's almost the opposite. And so we think there is a good reason why this is the case. Namely that these different flavors, for instance here, binary black holes, behave have a very different efficiency. So if you ask how many do you make, if you have different populations of stars, like how many of these pairs of black holes do you make to begin with? Then for binary black holes, we think you almost don't make them at high metallicity, but you kind of make them a lot at low metallicity. So there's this steep decrease. Whereas for neutron stars, we have a much more like flat distribution. And so this is interesting because it also means that when LIGO is seeing pairs of black holes or pairs of neutron stars, that it actually might be probing very different metallicity of stars, depending on its flavor. And so LIGO's black holes might actually be coming from a much lower metallicity population of stars, just because the universe is much more efficient at making pairs of black holes compared to like high metallicity stars. And it's interesting because, you know, that's just one example, but one of the other things that we're doing is to see these different flavors or these different uncertainties, do they also impact like many of the other different observables? So things like masses, things like spins, things like the redshift evolution. And it's very easy to give like another 2 or 3 talks about just those topics, but please ask me afterwards. The last thing is that like this stellar evolution, the stellar evolution is extremely uncertain. And one thing is in specific is that a lot of these population synthesis codes at their core still rely on the same codes for the single star evolution. So just if you have one star, how does it evolve? How does the core mass change? How does the envelope mass change, etc.? How does the radius change? And so almost all of these codes that I showed before relied on this one code from 2000 and 2002, so quite a while ago, that looks something like this, where it was basically an interpolation of stellar evolution grid. So this is like an HR diagram for just like, okay, if you have a range of stars, and this one actually only went up to 40 solar masses, how do these stars evolve? And so they all relied on this. But one thing that's been really nice to see is that there's a big effort in our community to now replace some of these stellar evolution tracks by things that are much more detailed and up to date. So there's a big group called Poseidon that is trying to replace them with like MESA tracks. That's shown here on the right, that you can already see it has like much more detail about how these stars should evolve. And there's also other work such as like Seven and like Matisse and Combine that's trying to make similar effort just to make sure that like our codes are much more up to date and are actually using much more of the detailed physics that we now know and can do with these codes. Yeah, and here's, for instance, an example for like why that really matters. So this is a result from Pooja and Agarwal from Matisse, where like, okay, if you replace these different stellar grids, so just how a single star evolves, you actually get very different results. So this is, for instance, these colors kind of indicate when in the binary there is mass transfer. So which time is there mass transfer, which is really important actually for deciding which binaries make a pair of black hole or not. And so you can see that like certain areas like this blue area completely disappear when you go from one code to the other. Of course, the overall goal I think that our group has is that like, yes, maybe currently we're here on the left. And so maybe this all sounds very pessimistic, but we're really working hard as a community to eventually go to this right picture where we can kind of like understand and quantify all these hurdles and eventually slowly overcome them and kind of like understand how to get to the end goal of using these gravitational wave sources to like really understand these massive stars. And it's actually nice. We're in a really good timing for this because we're kind of in this like era of like big data era of massive stars. And so for instance, for gravitational waves, here's a video that will show it, that as a function of time, we'll show you how many pairs of black holes, black hole neutron stars, and binary neutron stars we think we are expecting. And so right now we have about 100 after 03, but 04 is actually soon going to come out, 04A, and it's expected to basically like jump to like 300 at the end of 04. Then we're expecting to basically have like more than like several thousand by the end of 05. So a new observing run with LIGO, Virgo, and Kagra. But then the thing that we're really excited about is really these future telescopes like Cosmic Explorer and Einstein Telescope. Einstein Telescope might be built between Germany and the Netherlands and like Belgium. That are actually going to observe like hundreds of thousands of these pairs of black holes, black hole neutron stars, and binary neutron stars per year. And so if you do the calculation, like this is insane, right? Like there's not many fields that kind of multiply so many orders of magnitude in just the observations, like going from 100 today to like hundreds of thousands per year is there. And so if you do the calculation, then it actually of like Einstein Telescope maybe costs like a few billions or so. You can actually say that like Einstein Telescope basically becomes a unique instrument to study massive stars for just about $100 a star. Which is really cheap if you ask them as a star community. But there's a big caveat that is only true if you can truly connect these like gravitational wave sources back to learning about how these stars formed, lived, and died. And so I think that's a big challenge for the coming like 5 to 10 to 20 years. But there's of course so much more, because one thing that's important to note is that it's just not just going to increase the number of events by going to this new detector, but it also means that, for instance, if you look at the total masses of these pairs of black holes or black hole neutron stars, binary neutron stars, and currently with LIGO and Virgo, we can kind of see them up to redshift 1. So pretty far, but also somewhat near. But these future telescopes, like Einstein Telescope, they're actually going to detect these sources like all the way beyond like redshift 10. And so what this actually means, like these detectors are so sensitive, and this is actually how they get so many detections. What this basically means is that we're going to see every single pair of black hole, like stellar mass black hole, that's colliding in the universe each year. We're going to observe it. Like it's going to be a basically perfect sample, something that a lot of astronomers dream of. And then we might actually see if there's some, like POP3 or like primordial black holes out there that are colliding, that are basically formed before the first stars were formed. We might actually see it and see evidence for those kind of theories. So it'll be really nice, and it will be a really nice way of actually observing like different properties as a function of redshift for all these sources. And of course, there's so much more. There's gravitational waves has just started, so there's all these other wavelengths that you can look in. And for instance, especially LISA is probably going to find a lot of double white dwarfs and then some pairs of black holes and black hole neutron stars that are in our own Milky Way. So it will kind of be a completely unique way to study these sources. And then, of course, what's super important is there's so many other like surveys that are happening that are incredibly important for studying massive stars and kind of doing black hole paleontology. For instance, LSST is coming up very soon. That's going to detect a lot of cool transients and maybe some common envelopes and so on. But for instance, also Gaia is now finding some of these like systems that have like a black hole and a star, or like a neutron star and a star. That's been pretty successful. And so there's actually a lot of different areas that are hopefully going to really help out with quantifying some of these uncertainties and telling us how to get rid of some of our uncertainties in our simulations. And so here, for instance, two examples is that, of course, these same population synthesis simulations, you can also ask yourself, okay, besides just comparing to gravitational-wave observations, you can, for instance, compare to like pulsar binaries or these like LISA binaries that show up from the same populations. And so that will help and add a lot of constraints in the future to narrow down models. And so in the end, we hope with all these new observations and all this work that our field is doing, we can hopefully go to this step where we start learning and understanding and being able to really model like how do these stars evolve over time and what kind of gravitational wave sources do they leave behind. And so we hope that this will help open up this new field of like gravitational wave paleontology, where it allows us to then, by comparing to observations, go back and truly learn about like how these massive stars once formed, lived, and died in our universe. To truly learn about these massive stars and all their mysteries and all the mysterious things that they do, and especially learn about all these different processes that they have such an important role in. And with that, I'll just say that I'm starting soon at San Diego, and I'll be super happy to talk with anyone who wants to pass by or knows people who wants to pass by. We'll have we actually have 7 faculty joining in the fall. So there will be a lot of fun gravitational wave and massive star stuff to do. So please come pass by. And I'll just end with some fun other things we've been working on for fun recently, such as we made like a little software citation website tool that I hope people will like. With that, thank you. And I'll leave it for questions.
Okay, well, we'll have to make do with one microphone. I mean, that's a lot to get through one microphone, but thanks very much for that amazing forward look. I mean, we're certainly going to have a lot of different fields involved, and I can already feel there will be questions. I'll start by asking people from here in the hall to start. No? Students? Oh, one.
Hi, Flor. Great talk. So I have just one basic question that I'm curious. Well, I don't really need a microphone, but you mentioned several times this population 3 channel. I'm curious about how does this exactly work? It's like the binary isolated channel, but with population 3 stars, or? I have another question. Maybe I can ask both that you both, but okay. The other question is, if you expect so many sources with the Cosmic Explorer and the Einstein telescope, would you get to the point that you have like this background noise like in LISA with dwarfs?
Yeah, those are really good questions. So, okay, so for population 3, so all these formation channels, they kind of have to overcome what we call this like separation challenge, where like in the end, you need to have black holes that collide within the age of the universe so we can see them today. And so it actually turns out that you need to put the black holes pretty close together, like a few solar radii typically. And so like for population 3, how do you do that? So the trick there is that we think maybe at these extremely low metallicities, there's some theories that indeed you start with binaries of population 3 stars, and that these population 3 stars at such low metallicities basically can stay much smaller in radius than normal higher metallicity stars. And because of that, you can kind of form them closer together and keep them close together without them merging as stars when what they usually do when they expand to like 100 or 1,000 times their size. And so it depends on who you ask, but some say like, okay, it's kind of like the normal binary channel, but they just stay smaller, so they kind of come from this closer binaries. There's some people who still say like, okay, it's like you still have common envelopes even, or like still have all the like messy, even have dynamics maybe. But there's a lot of uncertain about how they form, whether they even form in binaries to begin with, because the binary fraction or binary function might be very different at those low metallicities, and how do they expand and so on. It's super, super uncertain. So it's a big open question. And yeah, I really hope we can observe maybe also POP3 stars in like other ways, so we can kind of confirm some of these like initial conditions about these stars. Now for the Einstein telescope question. So yes, this is true. So it's like we're going to find, you know, hundreds of thousands of events per year. And so this actually comes down to like, you know, an event every 30 seconds or 60 seconds or a few minutes or so. But one thing that's very interesting is that the main way that Einstein telescope can do this is that it hopes to basically push the frequency range to slightly lower frequencies, maybe 3 hertz if we're ambitious. And so this means that basically what happens if you have the frequency and then a binary starts at like lower frequency and then slowly spirals in and goes to higher and higher frequency until it merges. And so it actually spends like exponentially kind of more time at the higher frequencies than the lower frequencies. So like if you catch it in the last tiny frequency range, it's like super, it's just colliding. If you catch it like a little bit earlier, it's a little bit longer in band. So this is already why today often the pairs of black holes are only in band for like a few milliseconds, but then the neutron star mergers are in band for like a few minutes. These systems, we're going to catch them already at like a few hertz. And so they're actually expected to be in band for like almost a day or like maybe many days in some cases. And so there's a big problem if they're in band for a day and then you have one every 1 minute or 2 minutes. The nice thing is that you basically have like, you have a time that they come in and then a frequency. They all kind of enter at a different frequency. So although there's overlap, if you remember that I had this like plot with the chirp, there's going to be overlap, but they're kind of going to be like one here, like there's just 2D plots and they're going to like overlap, that there is a signal at multiple times, but they're going to be at like different frequencies and like different amplitudes. So people hope that because of that, there's actually not too much of a background, but we're not sure. And actually one of the issues is also lensing high in the universe, that a lot of signals might be lensed. So it might kind of cause extra background and noise. And so it's a big open challenge to kind of figure out how to deal with that. Yeah. Mm-hmm.
Hi, thanks for the talk. So I have a question related to the Agrawal paper, 2023, I think, where the authors compared sort of, I think, the fraction of case A, case B, case C versus single stars when one has the detailed modeling with MESA or so, and compared to the track outcomes. Perhaps you can comment more like what are the principal differences? I think in the detailed case, one has a suppression of case B binaries, right? So do you have any intuition why that is? So that is the first question. And second question, have you also investigated the effect that this makes on the binary black hole merger rates?
Thank you. I think also here one of the main differences is again like also the assumptions that you make lead to different like radial expansions of the stars, and that is like actually one of the reasons why I think here in some cases you don't have some of these islands that you have somewhere else. And then of course you see these like kind of sharp islands too here, which is a lot of the kind of just numerical ways that like poles entered where like there's more hard cuts, whereas because of also the pulse tracks, they really started with like a few star models, like 10 or so or 20 in each metallicity grid. So it's not that many. People haven't properly fully like looked into like, okay, how does this change all the binary black hole rates? There's been a lot of different codes that have calculated binary black hole rates. So in some ways that big review gives you some idea of like the range of scatter, but there hasn't been a lot of work yet in like this specific channel, and then asking, if you lose this island, which systems are you losing? And I think it's a very interesting question of like, maybe, if you find that binary black holes are always made, for instance, from kind of this parameter space, which could be true, then maybe you lose all of the binary black holes if you truly like forward model all these populations. There's work in progress. There's a lot of work in progress, like also by a lot of different people here as well, and like people comparing kind of MESA and so on. But I don't think there's like a fully consistent study that like does it. What the difference is between set 1 and set 2, I don't know by heart, but I can look it up and come back to you. Yeah, I have some notes. Yeah. Yeah, I forget what the exact difference is, but I can look it up and come back to you.
More questions from the hall?
Flor, thanks for the great talk. No binary neutron stars so far in O4, at least none with the electromagnetic counterpart. Maybe there will be something in the post processing analysis of the data, but I don't know. So do you think this may be a challenge for the rates that you showed? And also it may be kind of marginal intention with the rate that we extract from the pulsars in binary system in the Milky Way. So can you comment on that? Thanks.
That's a really good question. Yeah, so it's kind of been interesting, right? Because we had 70817, which was such a nearby double neutron star with like a kilonova. And so that really made the rate go up. And then we had one more binary neutron star. And then now there's been nothing in all of 04, or at least no alerts, which doesn't always tell you everything. So interestingly, it actually doesn't impact the rate too much. It's kind of by a factor 2. So they say now if in 04 you don't find anything, I think the rate kind of goes down by a factor 2, but that's okay. How much should you take that serious? Like is the question. And it's mostly because like this one event was so nearby that if you find that nearby event, it's your total rate of like as LIGO Virgo, if you say what's the total rate of binary neutron stars, is kind of dominated by that one nearby event, because the fact that you found one nearby means that there must be many more further away usually. I think it's true that it might be the case that like the gravitational rate of binary neutron stars might be much lower. I'm not too worried that it doesn't, even if it then doesn't completely match with the pulsar rate. Like the pulsar rate is super uncertain. It's like we have 20 binary neutron star pulsars. We don't fully know the selection effects of pulsars. So it's, I would say I take all the observational rates of binary neutron stars with like the uncertainty bars are probably like larger than even LIGO currently like admits, because even within LIGO, there's a lot of assumptions that they take into account. So they often have to assume what is the underlying mass distribution. So for binary black holes, they, for instance, they see nearby, they maybe see everything, but then at higher redshifts, they only see the massive events because they're so far away that you have to be massive enough, and otherwise LIGO doesn't see it. And so it means that how does LIGO calculate the binary black hole rate? Well, it says, okay, I found 20 things here, and I found 10 massive things here. So I guess there must be 10 low mass things also at high redshift. But we don't know. We don't know. And so there's a lot of these uncertainties about underlying mass distributions. There's a lot of assumptions about that the population doesn't really change over redshift, as well as other assumptions. So I actually wouldn't be surprised if the LIGO rate will still change quite a bit. And one thing that's been interesting is that LIGO has published, like after each catalog or each run, it has published a new rate for binary black holes, black hole neutron stars, and binary neutron stars. And the uncertainty bar has actually gone up. So usually you think, okay, the more systems you observe, square root of n, the uncertainty should go down. But actually in most cases, the uncertainty went up because what they did is they started including some of these like assumptions and varying them and calculating new rates and then finding like a kind of larger combined rate, which is kind of a funny thing. We should make a plot about that.
A question from Ralph and also one across here. I'll take Ralph first.
And further up, more exercise. Thanks, Flor, for this really great overview of the current state of the art and all the things that need to be brought into place to really move forward in this field. You gave a list of many uncertainties, essentially all of them astrophysical. And so I'm wondering about the identification of the wavefront itself, right? I mean, the gravitational or the relativistic hydro merger calculations, are these now completely under control, or what are the uncertainties on that side?
That's a really good question. So I think, actually I feel like from the LIGO perspective, we're kind of in some, it's kind of nice that like this field is really nice for like the observational perspective, that for instance, the LIGO selection function is, for instance, pretty well known. So like we understand well, like, okay, which masses can we detect to which distance and so on. So in many other fields, that's kind of a big problem of like, okay, which didn't we not see? But in LIGO, it's kind of an easy function of the masses, so that helps. The waveforms are going really well. So usually there's a lot of debate of like, okay, you want to do parameter estimation. And for individual events, there's large uncertainties. So when we see an event and we say, okay, what are the masses of this one event? People have like large uncertainties. Like sometimes you see 50 solar masses plus minus 20 solar masses. It's not uncommon, especially at higher distances. And so there, it's really hard. You really need more signal to noise ratio, I would say, is one of the biggest challenges. So like really having these future detectors that, at least for the nearby population, can have enormous signal to noise ratio that for individual events, you just know with certainty, enough certainty what it is. Because there's now a lot of these events like 1905, let's say if I say this correctly now, 1509-26, like the Boxing Day event, where like, okay, it's in the mass gap. So there's one black hole that's like kind of in this gap of masses where we don't expect black holes to be, between like about 40 and like 100 solar masses. And so it's kind of like, oh, this must come from this other formation channel. It's like what people will say. But then the certainty on that mass itself is still large enough that you can kind of straddle. So you can kind of say, oh, maybe it was a 30 solar mass black hole, and then it was just enough uncertainty, so you kind of push it in one way. And so I think on an individual level, that's still a challenge with the data today. But then already with 100 events, there's a lot of like this population analysis that we can do, where we can really say like, okay, but with all 100 events, when you really look at the entire population, you can start building evidence for some of these like theories. And you can start building, okay, we do see a lot of evidence that at least some events must be in that gap. Even if maybe for one event you could debate, there's still uncertainty that allows you to be outside of the gap. So I think that helps. For the waveform analysis, I think the biggest challenge right now is especially so most of the waveforms is fine. It's going to be a problem with these future detectors to have like dense enough grid that you're not biased by how dense your grid of waveforms is. At the moment, I think the main challenge is that we don't have good waveforms that do all of like eccentricity, precession, high mass ratio, and so on. So there's specific parameter spaces where maybe we don't have enough good waveforms, and we don't have good waveforms for like when they actually collide, like the post-merger phase. And so those are challenging, but people are working hard on them to improve on that. Yeah.
Yep, that looks like there's lots of very good things for theorists to do in the future. One last question to wrap up the question session.
Hey, yeah, you showed very nicely that there's many free parameters or knobs or kind of uncertainties to tune and change in these models. I guess many of them are degenerate and it's not easy to determine which ones should be on which values. I'm just wondering how do you deal with that, and how can we actually learn about these things, and what would be the way forward in the future? Better models by reducing the number of free parameters, better sampling techniques of sampling this huge parameter space. What do you think on that?
Thank you. That's a really, really good question. And so I think this is a hard problem, but I actually really believe this is a problem we can solve, not today, but like in 10, 15 years from now, I think we will have solved a big chunk of this problem, maybe not everything. And so I think there's two main things that we have to do. One thing that's, I think, the more challenging and more pessimistic about it, and it's you need to like look at like people like Ava, and so on, is that like there's really some detailed physics that these codes are completely missing, right? Like this common envelope phase, we're probably not, like all our models are wrong, that like we're just not even modeling or in the right modeling space. So you can vary your parameters as much as you like and combine, hyperparameters as much as you like, but that entire phase might be modeled wrong. And so there, I really hope we can rely on people who make a much better understanding of how this physics works, who maybe can come up with some grid of common envelope models or some prescription that is more reliable, or at least we can put more trust in. Big task. But and the same is like for supernova and things like that. Of course, the question before that is that we have to figure out which of these phases are important and are maybe most important, right? So one of the things that our field has to do at the moment, and that kind of goes to your other half of your question, is something I think we are working on and have to do more, is to quantify how important are these different barriers and these different uncertainties. So for instance, common envelope phase, something that's very recent debate in the past 2, 3, 4 years, is that classically people thought, okay, if you form them from pairs of stars, they always have to go through a common envelope. That's the only way to make them close and to form close pairs of black holes and then collide them. Now, recently, people are starting to say maybe actually the majority of pairs of black holes don't actually come from a common envelope phase, right? And maybe almost all of them don't never go through a common envelope phase, and stable mass transfer is enough to just bring them closer together. If that's the case, and we all somehow agree and come to the conclusion, okay, we don't need the common envelope phase, of course, we can we can get rid of all Javier's nice results, which of course we wouldn't do, and say like, okay, it's great that you're working on this, but you know, for us, it's not the most important phase. But we're still in this phase, I think, where, okay, at the moment we don't know, and we think common envelopes are very important, especially for binary neutron stars and black hole neutron stars. But I think it's an important part to like start quantifying, like, where should we invest our time in, especially because we kind of have 10, 20 years before Cosmic Explorer and Einstein Telescope come online. So we kind of have a little bit of time to do it. I think the other thing what you say is like, yeah, I absolutely think, and I think we have the resources to start really exploring all these uncertainties, because it is expensive, but actually the almost bigger challenge is to like how to visualize the results. Like we can kind of actually have the computational time to just run like a large grid, especially if you invest a little bit in machine learning methods and do it a little bit more efficient than usually. But a big question is like, okay, even if you run them, how do you start like quantifying, like, okay, how are these models different outcomes? How do they lead to different outcomes? Like, why do they lead to different outcomes? Like, what are we learning? How do they cluster in their results and so on? And so I think actually one exciting thing is that a big part of this effort is to even develop the kind of like infrastructure. And in my case, it's like, for instance, building a big catalog of simulations where you can analyze this or quantify, like, what does it mean if you change all these parameters and you see an outcome? Like, what does the outcome mean in like how it changes and like what we can learn? So yeah, I think it's actually a big like data science visualization challenge almost.
Okay, thank you. Well, I think we should wrap up the questions now. Before we thank Floor, I have some announcements to make. And the first one is that now is the time where we send out a call for proposals for speakers for next semester's Heidelberg Joint Astronomical Colloquium. So you will be, if you haven't already done so, receiving a message from your local coordinator in your institute asking you, and please everybody online and in the institutes, to make suggestions for speakers. And I think I've listed here the people in the institutes who will gather those suggestions. And if possible, I would like people very much to reply to their representatives by a week tomorrow to do that. So next slide. Yep. Next week we're staying in the domain of massive stars, and we'll have one of the prime movers of this field, Klaus Leithera, who was a long time ago also a member of the community here, to tell us about that as well. So we look forward to Klaus. And then last but not least, back to this evening, we have a dinner at Hemingway's. So Stefano, can you go and talk to Stefano if you want to join? And I think from about 7, is that right? Oh, it is 8. Okay. So you okay. Yeah. You gave up on French and Spanish participation. Okay. Anyway, so not 1900, but 2000, please get in touch with Michaela either here or by email if you want to come along. Okay, now Flor, thank you very much. You've given us a glimpse of an exciting future, and we look with great interest about how this is, at least those of us who will survive long enough, how this will actually pan out into the future. Excuse me, I meant that in a positive way. I think this is a really interesting field, and I have the feeling it's rather like planets in the 1970s. You know, there's a big jump to today, and I'm sure you'll manage it with all that knowledge and determination. Thank you very much.